今天非常高兴 ，It's my greatest pleasure to have a speaker here. 今天是何子山教授，他是美国艺术与科学院院士，美国天文学会会士，1990年获得哈佛大学学士，95年获得加州伯克利分校博士学位。然后3年以后，加入这个美国的著名卡内基天文台，成为一个资深天文学家。然后他2014年回到中国，任北京大学科维理天文与天体物理研究所所长，教授。I've known Louis for more than 2 decades. He is my resource. If you have any question, ask him how do you read this works? It makes sense for me. I go to him. So he has done so many work I cannot describe in just this here in 3 minutes. And his citation even 7000次 is modest. I just look at Google Scholar, 18,700次. Okay, so he's put a much lower number than the real universe. And his H index like 150 or something. It's crazy number. Okay, so that says a lot about his personal and scientific influence in the astronomy field, and he's not a part of a gigantic private team or simulated service, something like that. So these citations are real, okay, real citations reflecting his personal influence. He is the authority. 是我们研究这个黑洞这个物理过程的观测方面的这个专家学者。今天呢，我们总结这个以前的过去的30年的天文黑洞方面的观测，也有最新的这个Hubble Space Telescope 这个观测结果，小组里面第一次在讲，大家欢迎何教授。
Well, I think President is too modest himself. I'm just an observer, and whenever I don't understand anything, I ask him to help me as a theorist. But more seriously, I am enormously pleased to be here. This is my first time to the campus, this new campus of Zhejiang University. During lunch, when we were walking around, I told the professor that very, very honestly, I think this is the most beautiful campus of any university I've ever been to. And I've been to many universities. Really beautiful. I love the red brick, better than the red brick at Harvard. But more importantly, I am really happy to see the development of astronomy at this university. I came in 2019 when Hangxi and Kaohsiung, the two of them started astronomy group here. And in just a very few short years, even with COVID, now we have a very impressive group of astronomers from down to senior in competition. It's really amazing development. I think you have a very bright future. Because this is the School of Physics, and not all of you are astronomers, most of you are not, I will give you a very brief overview of what is an enormously important topic, which is the influence of supermassive black holes on the formation and evolution of galaxies. I used to think it's just the evolution, but today, at the end of my talk, I hope you might believe me when I say black holes may actually influence the formation of galaxies. I have been stuck in about 2 weeks. in preparing for this lecture because I've learned some amazing new things from the James Webb Space Telescope. I think we have reached a turning point, a new chapter actually, in understanding how the very first generation black holes were formed deep into the epoch of reionization. I'll share with you some of my thoughts. None of them are published. Okay, so you're the first to hear this. This is at the end of the talk. But let me first go back and take you through a little bit of history, ancient history. This is the oldest picture of the universe. It was only 380,000 years after the Big Bang, the surface of last scattering, so-called microwave background. It's remarkable for how incredibly smooth and homogeneous the universe is. One part in 10 to the 5. After 13.5 billion years or so of evolution, the universe is clearly extremely structured, not smooth at all. The structures here are galaxies. Each of these sources here is like the Milky Way, has a few 100 billion stars. Some of these most massive galaxies are 10 times, 50 times as big as the Milky Way. But because light travels at a finite speed, when you look at an image like this, you're actually going back in time. Okay. This very deep image with the JWST gives us an archaeological record of the formation and evolution of galaxies. This is the light emitted by stars through thermal nuclear fusion inside stars like the sun, starlight. Now I'll give you the same image, but in X-rays. This is 2 to 10 keV, non-thermal radiation coming not from thermonuclear reactions and not from stars, but from very, very high energy photons from hot radiation due to accretion of the supermassive black holes. Astronomers call these objects quasars, active galactic nuclei, but fundamentally they derive their energy from material falling into the gravitational potential of a very massive object. It releases heat, it releases radiation because the gravitational potential energy is being converted into radiation, into kinetic energy. When you reach the very center, there's a so-called accretion disk around the black hole. You reach temperatures that emit in the ultraviolet, in the X-rays, gamma rays, and you even have non-thermal processes that can give off cosmic rays. Okay. This picture of supermassive black holes generating high energy phenomena in the centers of galaxies was already established 61 years ago, with the discovery of quasars by Martin Schmidt, who was a professor at Caltech, worked in the Palomar Observatory. He was the first to understand or to interpret a spectrum. Okay, I'm sorry, I have to move around, so pardon the camera. Okay. This is a spectrum of a quasar, optical spectrum, that has basically 2 features. It has, you can see, a continuum emission that is rising towards the blue. That's because the accretion disk has a high temperature, a few tens of thousands of Kelvin, right? So there's a blue continuum. But you see these emission lines. These emission lines are due to hydrogen, right? Because the spark radiation photoionizes the gas, the hydrogen near the black hole. Polarization after some time leads to recombination, and you emit the spectrum of H alpha, H beta, H gamma. All the students know this because you understand the beforehand, right? But you see that these emission lines not only are very strong, they're very broad. The width here is a few thousand up to 10,000 kilometers per second. It's very broad because this is due to the Doppler motions of the gas around obviously a very massive object. Okay. So it's very broad because they're very large velocities. They're very large velocities because it's in the vicinity of a massive object. So this picture again, was established in 1963, and the interpretation was due to Salpeter, Lindenau, Martin Rees, and so forth. But all this activity happened early in the universe. Specifically, it peaked at a redshift between 2 to 3, we call it cosmic noon, when the universe was about 10 billion years old, okay? 3.5 billion years after the Big Bang. That's when most of the quasars existed. This is the number density, how many quasars in function. By today, by redshift 0, which here, okay, in the present day universe, they are no longer quasars. These are black holes are now basically asleep. They're dormant. Why? Because the universe has mostly exhausted its gas. Star formation has subsided, accretion has subsided, and this type of activity in the centers of galaxies are very, very weak or even absent. Okay, so they're just normal galaxies. But we expect that this picture is correct, that these nearby galaxies should contain in their centers these massive black holes, and we want to find them, and we prove that they actually harbor quiescent supermassive black holes. Let's start with the Milky Way, our own galaxy. This is an artist's conception of what the Milky Way looks like. It's a spiral galaxy, but we can't see this beautiful picture from this vantage point because we're embedded in the disk itself. So actually we have a very ugly and unclear view of the galactic center. The center is there, but you can't see it. It's obscured by dust. Okay, dust absorbs the optical light. That's why it's black. To get a clearer view of the center, you go to longer wavelengths. With the infrared wavelengths, the galaxy is more transparent. You want to zoom into the very central region at the highest possible resolution. Right? So the screen here is roughly a few light months. Okay? Not even a light years. It's maybe 3 light months is the diameter of the screen. And you want to take very sharp images so that you can see the stars. These are the stars around the center of the galaxy. To achieve this high resolution, we need to have some tricks, specifically adaptive optics. Because the light coming from the distant source has to pass through the Earth's atmosphere, which is turbulent, and that blurs the images. We call it seeing. Okay? So if you want to remove or correct the defects, you use adaptive optics. We use the biggest telescopes that we have. For example, the 2 10-meter Keck telescopes in Hawaii, in the north, and in the south, the 4 8.2-meter telescopes in Paranao, in Chile. This is run by the European Southern Observatory. And we fire these giant lasers, sodium lasers, 22 to 27 watts. Okay? Pretty powerful laser. Don't look at them, it's going to burn a hole right through your head. We shoot the lasers up to the atmosphere, they bounce back, and then we use that return signal to correct the waveform to get these very sharp images. And we take pictures of this very tiny patch again and again and again for about 25 years. Astronomers have been doing this for about 25 years. And what we notice, of course, is the stars are dancing around, they're moving. That's good, okay? But they're not just randomly moving, they delineate orbits, elliptical orbits. Just like Kepler and Newton told us they should. They're moving around something that you can't see. In the optical, in most wavelengths, it's absolutely black. I just put a star there, that's just an illustration. Right? So these stars are orbiting around an invisible object. What is the mass? Well, you can just use Newton's simple formula because you know the velocity and you know the radius, right? So for example, let's use this star, the most extreme one called S2. You see this thing? It's whipping around with a velocity of 2,000 kilometers per second. And the distance of closest approach is 1 light weak. Yeah, just smart, you can just work it out and that's 4 million times the mass of the sun. That's the central mass. That's pulling on these stars. That's impressive, 4 million solar masses. What's even more impressive is the implied mass density. The mass density, mass divided by the volume, is in excess of 10 to the 13 solar masses per cubic parsec. And those densities, it is essentially impossible to have anything other than a single collapsed object. Because you can imagine just having a cluster of dark things, right? Rocks, tables and chairs and brown dwarfs, whatever, okay? Neutron stars, even the elementary particles, they would evaporate or collapse on a time scale that is very short compared to the age of the universe. So this is a fairly convincing argument that whatever's in the center, even if we don't know what it is, has to be basically one single thing. We might as well call it a black hole. For this remarkable achievement, 25 years of patience and technological development, Reinhard Genzel and Andrea Getz shared the Nobel Prize with Roger Penrose in 2020. This discovery. This is a spectacular single case, but you cannot do a lot more because you need statistics. Most of the statistics actually came from this telescope. It's just a 2-meter telescope. This is the Hubble Space Telescope that's been operating in space for more than 30 years now. I was very lucky to be involved in using this telescope that had 2 primary key projects. The first is to measure the so-called Hubble constant, the expansion rate of the universe. The other is to search for and characterize supermassive black holes. Those were the 2 primary science goals. In the beginning, Hubble had some problem with the optics, which they were fixed in 1994. So in 1994, people were ready to use Hubble to really do especially the black hole search. I finished my PhD in 1995. And I was in the right time, in the right place, with the right people. They invited me to join the team that was responsible for doing this work. Included people like Scott Tremaine, like Rich Stone, Sandy Faber, John Conley, and so forth. And for the next several years, we had huge amounts of time given to us with Hubble Space Telescope to search for black holes. How do we do it? Very simple. Okay? Just, in China, you can learn this maybe, first grade, second grade, right? Okay? It's just, you just use a Kepler's law. Okay? So you can measure the velocity as a function of the radius. Okay? The velocity goes as the 1 over the square root of the radius, and it depends on the mass. Okay, so this is how we get the mass of the sun. If we didn't know the mass of the sun, you measure the velocity of the planets as a function of the radius. You can solve for the mass of the sun. So we do this for galaxies. We measure as a function of the radius, the velocity around the center. We want to get as close as possible because we want the gravity to be dominated by the black hole and not by all the stars around it. So we need to reach very, very small radius. That's why we need to go to space. We go to space because this telescope doesn't have steam, doesn't have the atmospheric blurring that we need to correct with adaptive optics. It's above the atmosphere. Okay? So that is just the simple trick that we do. And there are 2 tracers that we use. Okay? We use gas. In the center of a galaxy, there's gas, hydrogen. If the hydrogen is ionized, it emits H alpha. This is a combination line. This is a classic signature of a rotating disk. And this is velocity on the x-axis, distance on the y-axis. So on this side, this object is very blue shifted. It's coming right at you. And that side, it's going away from you, right? So blue shifted, redshift, blue shifted, redshift. This zigzag signature is a signature of a rapidly rotating, rapidly spinning disk. Again, using the formula, we can work out the mass. In this case, it's 10 to the 9 solar mass. not 4 times 10 to the 6, it's 10 to the 9 solar masses, and it's absolutely dark. Okay. Now, this is a galaxy. Not all galaxies today have gas, but they all have stars, especially the bulge region. The central bulge of a galaxy is full of stars, but it's the same thing. Now we're measuring the velocities of the stars. Okay? This is the radial velocity, v is a function of radius, and this is the velocity of dispersion, the random component of the pressure supported component of the skeleton component. Same thing, you can very easily actually just work out the central mass. And what we were really surprised after 1 or 2 or 3 years of a few years of observation is that, we had a lot of time. We observed many galaxies. Every single one is detected. Not a single upper limit, not a single failure. Every single galaxy, every single bulge had this signature of a central dark massive object. This exceeded our expectations. We thought we would find some massive black holes. We didn't expect to find it in every galaxy. So that was really a bit strange. It's much like a peach always has a pit. The black hole is always associated with the bulge of the galaxy. It's a relatively massive galaxy. Let me update you when it's happened just very recently. In China, you heard it in the news, okay? Also, there's confirmation that the mass is incorrect, but just for fun. Okay? So one of the galaxies we declared earlier is M87. This is one of the biggest galaxies near us. It's in the Virgo cluster. It's a giant elliptical galaxy. We use the Hubble Space Telescope to obtain, by this technique I described, this mass, okay? 6.2 times 10 to the 9 solar mass. Very massive, 6 billion times the mass of the sun. This is more than 1,000 times more massive than the black hole in the Milky Way. Recently, radio astronomers use a very clever technique of interferometry, radio interferometry. The essence of the technique is to combine the signal from a network of telescopes around the world. Why do you want to do that? So we want to increase the resolution because we want to go as close as possible to the center. How do you do that? Oh, you guys study basic physics, right? The resolution of a lens is lambda over d. Lambda over d. So you want to make lambda as small as possible. You want to make d as big as possible. So lambda is the wavelength. So you want to go to high frequencies. Okay. Small wavelengths, short wavelengths, high frequencies. So we go to millimeter, sub-millimeter wavelengths. Okay. And we want to make d as big as possible. So let's make d the diameter of the Earth. From the South Pole to the Greenland, okay? To achieve exquisitely tiny beam, high resolution, and then you wait for the no. Yeah, okay. You wait for the Earth to rotate. As the Earth rotates, you're basically filling in this giant aperture, so it's what's called aperture synthesis. You're making an aperture, you're synthesizing an aperture. And you create an image. This is a famous image everybody's seen. It's called a first image of the black hole. Right? What it is the emission here is coming from the vicinity of the black hole, near the black hole, and it's being bent by gravitational lensing into this donut. The center is literally dark. Now, the size of this donut, this radius, is none other than some multiple de Schwarzschild radius. It depends on the spin of the black hole. But simply by measuring the radius of this donut, which is linearly related to the mass of the black hole, you can infer the mass of the black hole. And very happy to know that it's very similar to what we have obtained with the Hubble Space Telescope many years before. 6 billion before. So, okay, that was just a detour. Let's go back to the statistics we had accumulated already in 1998. Okay, for 5 years, we have enough objects we can make a diagram, which is the mass of the black hole versus the mass of the bulge, the stellar mass of the bulge. We were really kind of shocked to find that they fall on a single, extremely tight linear relationship. It's been since called the Magorian relation because of the first author of the paper. Basically, the mass of the black hole is a constant fraction of the mass of the stellar mass of the bulge, 0.5%. It's a tiny amount, okay, less than 1%, but it's like a universal constant. This is extremely strange. You might think, okay, what's the big deal? It's just bigger is bigger, right? Well, not really. This is really big. The galaxy is really massive. This is really tiny. Okay? Why do they know about each other? The galaxy surely cannot care about this little thing in the center, right? And this little thing in the center has no gravitational effect on such large scales. Okay. So it's really mysterious, but it's even more mysterious. 2 years later, we published this diagram now called the M sigma relation. So now we have the mass of the black hole on the y-axis, and on the x-axis is the so-called velocity dispersion of the stars in the bulge. Okay, this is the random motions of the stars in the bulge. This is on a very large scale, many kiloparsecs. Okay, so tens of thousands of light years. It's even more strange because this x-axis is not a mass. Okay? Mass, you need a size. Okay, right? You need a size. There's no size here. It's just the velocity. What's going on? Again, very different scales. The size scales are totally different. This is AU scale. This is the Schwarzschild radius of the black hole. This is tens of kiloparsecs. Sorry, yeah, many kiloparsecs. Okay, so hundreds of thousands of, tens of thousands of light years. Okay, vastly different physics, even because you involve galaxies that form through mergers, like giant ellipticals, to galaxies that have very little mergers, like spiral galaxies. Different physics, different evolutionary pathways. After Hubble time of evolution, they all line up on a single, nearly perfect correlation. Nobody really understands. Many people think they understand, but nobody can agree on what is the basic physics that is driving this. That is the reason that these 3 papers that I listed up there have, as of today, 11,000 citations. Many people have thought about it, talked about it, used it. Okay, they think they understand. The basic idea is as follows. Even though the black hole is tiny, like the galaxy, it releases energy very efficient because it's gravitational energy. It takes m dot c squared and releases it over very short time scales, or saltpeter time scale, a few million years. Okay, m dot c squared is a very large number compared to thermonuclear reactions. Okay, so that's the basic idea that the black hole, even though small, can release a huge amount of energy, maybe enough to unbind the gas of the galaxy. Galaxies form hierarchically. When they merge, a huge amount of the interstellar medium gets driven to the center of the galaxy, where most of it forms stars, but some of it grows a black hole. The black hole therefore releases, you watch the galaxy explode right there, okay? It releases energy so efficiently, so much of it, that basically it can really affect the interstellar medium, the gas in the entire galaxy, enough to control star formation, shut off star formation, self-regulate accretion into the black hole. This type of feedback loop. This idea of HN feedback is now a very popular idea. that is basically encoded in many of the theories of galaxy evolution. This is what happens for the radiation or photons. Some of these black holes are even stranger. They release not so much radiation as kinetic energy and momentum, because they square out relativistic particles, create synchrotron radiation because you're in that field, and you have fast-moving electrons. These jets vastly exceed the scale of the galaxy. This is the galaxy. They can go up to megaparsec scale, millions of light years. They affect not the galaxy so much, but the environment around the galaxy. Okay, so this is a picture. In blue is the X-rays showing the hot gas around this giant galaxy. The red is the radio jets. You can see that the jets create these bubbles in the X-rays. Okay, clearly showing that this type of feedback can really affect the environment around the galaxy. Also, many current theories of galaxy evolution claim. In fact, they claim that without this, we cannot understand many of the challenges in galaxy evolution. For example, the star formation is a function of time, a function of cosmic history, has this peak as well around redshift 2. It rises and then it falls. Just like the quasars, I told you. Okay? Quasars rise and they fall, and the peak is around the same place, the cosmic noon. Okay. Otherwise, it's very hard to understand why star formation in galaxies is so incredibly inefficient. Roughly 16% of the mass is in baryons. Okay, so cosmic baryon fraction. If you convert all of the hydrogen, all the baryons into stars, okay, the ratio of stars to dark matter should be 16%. But no, okay, if you look at this is the ratio of stellar mass to dark matter as a function of dark matter halo mass. Even at its peak, which is around 10 to the 12 solar masses, this is only 3%, 2 to 3%. And if you go to low mass galaxies and high mass galaxies, it's even worse. So what's happening? What happened to all the baryons? Why are they refusing to cool efficiently, to make stars efficiently? The story is that something is preventing them from cooling efficiently. Something is heating them, delaying the cooling. Okay, apparently you must have HN feedback to realize this. And then there's the fact that galaxies are bimodal. They're sort of on and off. Okay, most galaxies they are on, they're blue, they're forming stars, and then some are dead and basically gone to sleep. And it's on and off. Okay. Apparently, in order to turn star formation off, you need a very efficient feedback mechanism, and the most popular one again is HN feedback. So I make these points simply to tell you that black holes have become extremely popular as a mechanism for interpreting many of the observations that we know about galaxies today. Okay, but these black holes that I've been talking about, measured with Hubble Space Telescope, again, are found today in redshift 0, and they're really completely inactive. If we want to understand how these connections arose, we have to go back in time. We cannot just stay here in the local universe because all the action is already gone. We need to go back in time. We need to go back in time when these black holes were quasars, when they were actively accreting, actively growing at high redshifts, right? But how do you do that? How do I measure the mass of the black hole in these distant quasars? First, they're very distant. It's at redshift 2, and 3, and 4, 5, 6, okay? No way, we will never observe them directly by resolving them. There's no telescope that has a resolution that can possibly get that rotational curve all the way to the center. So no spatial resolution because they're so distant. Secondly, the quasar is very bright. It's like having a giant light shining right in your face, okay? You can, so bright that you cannot see the stars underneath, which is completely outshined by the quasar. And even if there's gas, you should be suspicious because radiation pressure from that bright quasar will push the gas around, okay? So the motions of the gas is probably not due to gravity. It's due to shocks, due to radiation pressure, whatever, the magnetic fields, okay? You cannot interpret confidently the gas kinematic. So how do you estimate the mass of the black hole? Let me give you a tiny detour into a technique that we've developed. And I also helped develop this observationally since I was a graduate student. So it's, we're not going to measure the mass of the black hole, but let's estimate it. And I'm going to show you we can estimate it to, I don't know, factors of 2 to 3, 0.3, 0.5x, okay? The principle is very easy. We want to measure two quantities, R and V, in order to get the product, which is the virial product, right? We want to estimate the virial mass of the black hole. It's a fudge factor F because we don't really know what is the geometry and the inclination angle of order unity. G, this is just the quotation. Okay, so how do we estimate R and V? Well, this is a schematic of what a quasar looks like in terms of its basic components. So around the black hole is what I call the accretion disk. Remember that, right? That blue spectrum. Okay? The accretion disk is hot, rises towards the blue. It's coming from the accretion disk. And I told you that you have emission lines that comes from gas. We call it the broadline region because the lines are broad. It's due to the reason they're broad is because they're moving around this gravitational potential of the black hole. So that's easy. If we assume that the velocities really are due to gravitational motions, then the width of these emission lines gives you V. Okay, so V is easy. Once we take a spectrum, these are broad lines, we measure the line width, that's V. The hard part is R. We cannot resolve R because these objects are too far away. Okay? But we're lucky because these quasars, the continuum emission from the accretion disk is not steady state. It's not constant. In fact, it fluctuates. It goes up and down, up and down, up and down. Why? Because the accretion in the disk, okay, the accretion is not constant. There are little fluctuations, there are little weather patterns, there are little instabilities. So the energy fluctuates. Okay? So the blue ultraviolet continuum goes up and down. Okay, this is the luminosity, it's a function of time. But also the broad emission lines, the H beta also goes up and down and up and down. Yes, because it's just reprocessing this continuum. Yes, H beta comes from photoionization by this continuum. So of course, they should follow basically the same pattern. But if you have good eyes in the back of the room, you can see that they're shifted. These light curves are slightly shifted. There's a delay. There's a lag. You don't need to use your eyes just to do a cross-correlation analysis, and you'll find out there's a lag, okay? a delta T. And the delta T is just related to R by the speed of light. So this lag is basically the time delay between the accretion disk and the broadline region. So with this method, we can basically resolve the broadline region not spatially, but temporally. We call it echo mapping. More formally, sometimes it's called reverberation mapping. The broadline region reverberates. So this is how we obtain the mass of the black hole for active black holes, for quasars. And we can do this with 0.3, 0.5 depths of accuracy, essentially at all redshifts, from local redshifts out to extremely high redshifts. Okay, I hope you got that, okay? Now, I'm going to show you two important applications of this technique and lead you to the topic of sea black holes and the formation of the first black holes. So let's get back to this famous diagram. I want to ask a basic question. What is the lowest mass black hole that the center of a galaxy has? What is the seed of these supermassive black holes that we find? Okay? What were the initial conditions? How big were they? For the purposes of this talk, I'll divide the black holes into two just categories. The supermassive objects tend to be 6, 10 to the 10 solar masses, and the intermediate mass objects say 10 to the 3, 10 to the 6. We know that stars can make black holes too, not the sun. The sun will end its life after another 5 billion years as a white dwarf. But if you're more massive than 8 solar masses, stars explode. We call them supernovae. And depending on the mass of the star, okay, they either end up as a neutron star, or the more massive ones would end up as a stellar mass black hole. Stellar mass black holes have a mass range of a few solar masses, say 5, up to about 80. This is what we learned from LIGO, from gravitational events from LIGO. Okay? So the spread is very big. But the upper limit is about 80, 60 or 80. This is what we call stellar mass black holes. But we're interested in these more massive seeds, not stellar mass black holes, but the massive seeds that make essential black holes in galaxies. And they're very essential, not just for understanding quasars, but for understanding, for example, cosmic reionization. Okay, very first generation massive black holes, did they contribute to cosmic reionization? There are two channels that people talk about making these seeds. This might call the light channel due to population of 3 stars. First generation extremely massive stars. They could leave seed black holes of say 100 solar masses, just through normal star formation. Maybe more exciting and very, very speculative are so-called direct collapse black holes. They directly collapse from giant gas clouds which do not cool efficiently, do not fragment efficiently, because they're very few metals. They're almost metal-free early enough in the universe. And according to numerical simulations such as these, you can make these heavy seeds that could have initial masses of 10 to the 4, 10 to the 5 solar masses. Okay, so this was already proposed a long time ago, I believe after in the 1990s, but they're mostly a theoretical construct. But I'm an observer, I'm an experimentalist, and I want to ask, can you actually find these things? Is there any evidence for these low mass seed black holes, intermediate mass black holes in the universe? Let's begin with the local universe, which I know the best, and ask, where are they? Where would you find them if they existed, these intermediate mass black holes? Well, no, don't bother looking in those objects. Okay, these are galaxies that are massive, that have a bulge. We already found all the black holes. I told you that 100% of them have black holes. So there cannot be seed black holes hiding in these massive galaxies. If they exist, they would be in these objects, these dwarf galaxies, bulgeless galaxies, these low mass galaxies. But I cannot measure the mass of a black hole by direct dynamical techniques. I cannot resolve their tiny sphere of influence. Instead, we're going to look for them by looking for little quasars, mini quasars. Okay, just like quasars. I think quasars come from accretion onto a black hole. So if they're smaller black holes, they will just be little mini quasars. This I know how to do. In fact, I did that as part of my PhD. My PhD involved a survey of the 500 brightest galaxies in the Northern Hemisphere. I used the biggest telescope in the world at the time, the 5-meter, got more than 130 nights of observations. And the main result was that the majority, up to 80% of these early type galaxies with a bulge, have this little quasar in the center. That's good. Okay? That confirms, in fact, predated the result that all bulges have black holes. Vast majority of bulges have this accretion in the center. But notice that the fraction of black holes is not 0 for these late type galaxies. It's in fact about 15%, 10 to 20%. Okay, so these very late type, very low mass, bulbous galaxies, in fact, have AGNs in them. Here are two of my favorite examples. And you see 4395. It's hardly a galaxy, right? It's so low surface brightness, so fragile. At the very center, if you take a spectrum with the world's largest telescope, it has these broad 1,000 kilometers per second emission. That's the even more extreme example, Fox 52. It is the size of only 1 kiloparsec. It's a tiny dwarf galaxy. It has a spectrum just like a quasar. But look at the mass. It's 10 to the 4, 10 to the 5 solar masses. Okay? So I knew of two examples. Two is good. Two is better than one. And one is better than zero. Audience, no reaction. Okay. One means that nature can at least make it. Okay? It's a proof of concept they exist. Two means that you didn't screw up. Right? Okay. But two doesn't make a science. You need not 500 spectra of 500 galaxies. You need 500,000 galaxies. 1,000 times. That's what the Slow Digital Sky Survey, thank you very much, gave us in 2004. Suddenly I have 500,000 good spectra like these. Okay? And you can search again this signature, these broad emission lines. Well, it took me many years to analyze 500 galaxies. Now you give me 500,000. How could I possibly do it? Well, you get a graduate student who is smarter than me. Her name is Jenny Green. She came from Harvard, and this was her PhD thesis. Okay, part of it. In this giant survey, she found it was not two, but 200, 500. Now we have a subject. This is a very important work that Green did for her PhD thesis. Besides finding them, we get many other works. The most important thing is to take pictures of these new class of objects, really absolutely new class of objects, to show how incredibly interesting the galaxies are. They're tiny things, they're dwarf galaxies, they're late-type galaxies, they're bulbous galaxies. What does that mean? These galaxies, even though they're tiny, even though they're low mass and dwarf galaxies, they were not formed yesterday. They are oldest galaxies in the universe. The reason that they're small is because they never grew up. These are the galaxies that never merged. In fact, they preserve the memory, the initial condition, right? This is what galaxies were like in the early universe, but we find them here now. And the black holes that they have in the center also are the fossil remnants of their formation before. They just never grew up. I hope you understand that. So this is why this class of objects is very important. But that's only, a few hundred. Okay? Well, are there more? Are there more in these things? To find more, actually, a better technique is to go to the X-rays. Those are optical. Okay? This is the Chandra X-ray satellite. There's almost zero noise in its amazing detectors and has sub-arc-second resolution. And Chandra is amazing because, look, this is a picture, the optical picture of a nearby galaxy. It's really beautiful, right? There's these spiral arms and, all these bright star-forming regions and these dust lanes. Right? It's precisely because it's so beautiful that it's awful to try to find anything. If there's a tiny little quasar, where is it? Somewhere in here, okay? But how do I find it, okay? It's contaminated by all of this extra crap around it. Go to the X-rays and, that's the picture. You see all the stars that disappear, except a few X-ray binaries, which are stellar mass black holes. And in the center, there's a big black hole. So X-rays, high resolution. Beautiful, okay, that's 2 kiloseconds, one snapshot, I removed all the contamination, and I can just search for the thing, okay? And I did this with 3 generations of PhD students. Now we have roughly 2,000 galaxies, and we found a whole bunch of these things. Okay, these are, again, very late type, bulbous dwarf galaxies. They all have this X-ray nucleus. Okay, many other examples. All of these things were missed in the optical. You only find them in the X-ray. How many are there? 30%. Oh, okay. Give me 1 second. Okay. So the detection rate among late type, low mass galaxies is 30%. Really common. In fact, that's a lower limit. So this is the conclusion from my annual review with Jenny Green, that the occupation fraction of these intermediate mass black holes is in fact at least 50%. At least 50%. Okay, so we've proven that they exist. They live in low mass galaxies. In fact, they're very common. They're at least 50%. But we couldn't tell back in 2020 how to distinguish between these two channels of formation, light versus heavy seeds, population-free stars or direct collapse. I'm going to show you now that I think we can with JWST observation. Okay, so first, we've answered this question. Do they exist? Yes, absolutely. Where are they? Slow mass galaxies. Okay, fine. Okay, so now let's go to the very high redshift universe. Okay, so redshift 6, we've known for a long time. We can find quasars. It's very hard. They're very rare. Okay, we can use special color selection, whatever. All over the sky, every 10 years, you find one of these things. Okay, so we should make after a lifetime of work. Found this extremely gargantuan black hole in redshift 6.3. Already the black hole mass is 12 billion solar masses. This is the record holder up to now, redshift 7.6 billion solar masses by one figure. That's it. Okay, this is really rare. But they're really important because these masses are huge. 10 to the 9, 10 to the 10 solar masses. And the universe is less than 1 billion years old. So we want to know what was the first generation seeds that grew up to these sizes, because you have no time. You have so little time. You have started with a population we see to grow up to these extraordinary masses. Let's solve this with JWST. Let's just keep going. Let's just go all the way out to redshift 20. Okay, that's where the first generation seeds would be, somewhere in this unknown new territory. Okay, what are these things? Okay? First generation quasars. Here are some papers in case you've missed them. These are all in the last 3 months. And believe me, this is only roughly 30% of all the papers. Okay, these are the ones I could read before my trip. Okay. You don't need to know them in detail. Just look at the titles. Okay? They're like really, really exciting. People are finding something exciting and something odd at these very, very early epochs of JWST. What did they find? This is the data that they use. Okay, this is data from the James Webb Space Telescope. 7 filters. Extremely high resolution, extremely deep. The phenomenon is called little red dots. If you remember nothing else from this talk, remember those 3 words, little red dots. And I will argue, and I will hope persuade you that these are the progenitors of quasars. In fact, they tell us what is the formation mechanism of the first quasar seed. So what are they? So here are the pictures. Little red dots. They're red and they're really, really tiny. Some of them have stuff around them, but many of them are totally isolated. But by the way, this phenomenon was coined and discovered by, guess who? Jenny Green. She's one of the key people in one of the teams that have done this work. What are the characteristics? I want you to help me appreciate this. They are really tiny. They're unresolved. On what scales? Less than 50%. It's upper limit. It's unresolved. In one case, a few cases that are gravitationally lensed, the size is even smaller, 30%. Now I'm going to ask you a question. Do you see a galaxy around these things? I know. Another very important fact is that the spectral energy distribution, the spectrum, is a V. It has a blue tail and then there's this red thing. It's a V shape. This is a very characteristic. All of them look like this. Red and blue. Two components. Now, all of these authors, they interpret it in this way. They say, well, there's a quasar in the center that's obscured by dust. That's why it's red. And then there's some fraction of the light is scattered out. And some, the dust is not complete, and some of it scatters out. So this is due to scattered light that's leaking out. That's why you have this characteristic. I disagree. I strongly disagree with this interpretation. You see, if it's dust, that's an accidental thing. That's an environmental thing. It should be a little bit and more, covering factors, 10%, 20%. So it's scattering. It's an accidental thing. We should not produce a universal V shape. I propose this is intrinsic. This is an intrinsic spectrum. You guys figure it out. Okay? Somebody like you, right? Oh, by the way, they have no X-rays. Isn't that interesting? Okay? Just like low beams, X-ray meet quasars. They could have been detected, but they're not detected. Okay. How do I know that they're AGMs? Look at the spectrum. Amazing thing with NMST is that you can take spectrum in addition to these gorgeous images. They all look like quasars. Look at these broad lines. They just look like what I showed you earlier, right? Okay? Thousands of kilometers per second. The implied masses are 10 to the 6, 10 to the 7, 10 to the 8 solar masses. They're emitting near the Eddington limit and have extremely low gas methodicity. Very, very low gas methodicity. First generation type of conditions. Okay? But they're really abundant. How abundant? It's 100 times the abundance of quasars, and nearly 10% of all galaxies. This is the green line here is the luminosity function of quasars. It stops, right? This is the previous limit. This is the extrapolation to fainter magnitudes. The little red dots are several hundred times more numerous than the quasars. The blue line is the mass function for all galaxies. You can see that they are approaching. Okay, this is a few percent. In that study, it's 10%. But this is just the detected population. There must be more, right? There must be something obscure. Okay, so basically, we're approaching 100%. Well, why are you surprised? I told you in the nearby universe, all galaxies have black holes, didn't I? All the massive galaxies have black holes, and at least 50% of the low-mass black galaxies have intermediate-mass black holes. You're in deep thought, can't see anything, right? All, to zero order, all local galaxies, the vast majority have black holes. Well, they have to have been formed somewhere. You're looking at them. This is the first generation black holes being formed in the earliest generation galaxies. The abundance is approaching the full galaxy population. But they are overmassive. They completely violate my cherished local relationship, okay? This is a local relationship for dead black holes, inactive galaxies, right? I told you, 0.005, 0.5%, very tiny scatter. This is for inactive galaxies, the redshift 0. This is active galaxies in redshift 0. These are AGX locally. Okay, basically they have roughly the same ratio. The scatter is a bit larger, okay, but basically they have the same ratio, 1%, 0.5%. And redshift 0, black holes make up 0.5%, 1% of the total galaxy. And these redshifts, for these little red dots, are too high. By a factor of 10 to 100. All those points, okay? So this is the local ratio. This is the population. This is an absolutely astonishing result. Clearly, it's telling us that the black hole formed faster and possibly before the stars. The stars in that ratio, those are lower limits. I'm sorry, upper limits. I don't see them. So that ratio is a lower limit, right? This has incredibly serious consequences for whatever ideas you have about, feedback, coevolution, What feedback? What coevolution? Nothing is co-evolving. I see the black hole, I don't see the damn galaxy. Okay. So this long-standing puzzle, okay, how do you get from the seeds to these gigantic black holes at redshift 6 and 7? The trouble has always been that if you start off with 100 solar masses, population 3 stars, in order to get up here, you need to accrete at super Eddington rates. Okay? Super Eddington rates. Otherwise, you can't get there. And you need to accrete at super Eddington rates for hundreds of million years continuously. Otherwise, there's no way you go from 100 to 9. However, if you start off with a more massive seed, either from a dense cluster or from direct collapse, then you can go up there, by more reasonable. Well, haven't we just discovered this? We've solved this now, right? Okay, so here's redshift 8.9, okay? Okay, there it is, 8.9, okay? There's no way you can go up there by a population of these stars. Okay? You can. You have to start off at redshift 20 and accrete at super Eddington rates, or you can just go up there more casually, say redshift 15 or so. This is the object I placed on this diagram. Okay, it's overluminous, overmassive compared to the galaxy, just like all of their friends, all the other little red dots. They're all overmassive. But this is completely what you expect from direct collapse. Direct collapse means you just worry about yourself, right? You just make the thing, okay? And then the stars may or may not catch up later. That's their own business, okay? This is it's like a rigorous argument, but this is what I think of direct collapse to be, right? Let me bring back this picture, and I want you to seriously look at it. Again, this scale is 30 parsecs, 50 parsecs. And this is a very, very deep area. Let me ask you, are you sure there's a galaxy? Are you sure there are any stars? Okay. My students are very, very busy now trying to quantify this, okay? But I think maybe there are none. Okay? These are lower limits. Well, that's very exciting. I think this is the most exciting thing I've ever read and studied, since I was, in graduate school, okay? Since we first discovered the instinct relation, okay? Okay, let me finish. All of these galaxies have sea black holes, various types, okay? Most of them do. Big galaxies have them. Galaxies merge, different types of mergers. Very unequal mass mergers, right? 10 to 1, 100 to 1, 1,000 to 1. It's going to make gravitational waves, exactly as in the frequency band that would be needed to be detected by LISA, by China's Taiji and Tianjin. Okay, and the more massive ones also have timing delay. As many of you know, in the last few months, there's already an announcement of international collaboration, particularly from China, using FAST, of a 4.6 sigma measurement of the stochastic nanometers gravitational background, which is very likely due to merging supermassive black holes. So we think the timing is wonderful. This is going to be, unless there's an earthquake in Huzhou, okay, I think this result belongs to China. Okay, 4.6 sigma is the best result compared to Demograph or to international pulsar time delay. Moreover, we know that China has a very ambitious space program. It's already launched and assembled the space station. It's been operating for quite a while now. Importantly for astronomy, in 2026, there'll be a telescope, the CSST, China Space Station Telescope. Like Hubble, it's a 2-meter telescope, but unlike Hubble, it has a camera that is 350 times bigger than Hubble. 350 times bigger than Hubble. And unlike Hubble, which is a PI, driven thing, this is what dedicated to survey 40% of the sky. I think it's extraordinarily exciting. These are data from Hubble Space Telescope. We will have images like this for billions of galaxies. There will be billions of galaxies. There will be millions that have very good resolution, okay? Multicolor, even slit spectroscopy. So this is going to be completely revolutionize extragalactic astronomy, especially since the NASA Roman Space Telescope will be flying at the same time. The infrared, optical, the AUD. Therefore, I'm extremely happy that we have several science centers set up for the CSST, but the one that's responsible for galaxies and AGMs is my institute, the Cloud Institute in Beijing. Okay, so let me finish. I'm sorry I went a little bit long. I want to explain this clearly. First time I'm getting this talk. The discovery of central black holes, I think it's been well established for 25 years. We've shown that they are fundamental constituents of galaxies. Black holes are said to co-evolve with galaxies. The energy feedback from black hole growth can significantly influence the evolution of galaxies. The statistics are quite astounding. For massive galaxies, supermassive black holes, 10 to the 6, 10 to the 10 solar masses, it's 100%. Occupation fraction is 100%. Low mass galaxies, it's at least 50%, with the intermediate mass black holes in this range. We've known for a long time that quasars can come from supermassive black holes 10 to the 9 to the 10, even when the universe was really young, less than a billion years old. What is really new, incredibly new, okay? By the way, most of those papers I showed you, they're not yet published. They're all on the archive, still being refereed. There's a population of early black holes, early quasars, 10 to 6, 10 to 8 solar masses being discovered up to redshift 11. I think this is one of the most important and consequential recent developments, as consequences for many things. Our understanding of how black holes formed in the first place, for cosmic reionization, okay? We need to reconsider everything. There are a lot of them, and their spectra are very different, okay? And of course, gravitational wave astrophysics. There's much to do observationally, theoretically, analytically, numerically, cosmological simulation, go have fun, okay? So, for the few students in the audience, I just throw up a few references in case you want to read about these things. Not from JWST stuff, just about the early points. All right, so thank you very much.